It's 11. Are you ready? Okay. Please do the homework. Who didn't get the hard copy of the homework? Hard copy of the homework. Please raise your hand. Okay. First, we will start at the correction. Okay. One, and I already upload all these, okay, on the blackboard. The correction that I have for the AGA isothermal flow is that in the previous one, I forget to put number 2 over there. And the updated version, I put number 2 over there. I think it's matter because it's an exponent. Okay, that is the exponent. That's number 2. Good. You got this for HA isothermal flow. Okay. All right. Another correction is the next correction is. It's not quite a correction, but I add something more this morning. Okay. It is a guideline for the pipeline to gas plant. Okay. For Anton-Irish gas cell, we have multiple well go to the tank battery. This is just a guideline. Okay. You can do something else. So multiple well go to the tank battery. I'm talking about the gas, okay? Gas from well to the tank battery, and from the tank battery, it's have 1 to 5 line, and then gas to the fuel compressor. From the fuel compressor, then gas go to gas plant. There can be multiple battery connected to fuel compressor. This for Anton-Irish. For Eagle Ford, gas can go to battery, and battery go to the gas plant, or if you have satellite, it will be from satellite directly to the gas plant, because Eagle Ford, that field, the gas has high pressure. Okay, and the distance between well and battery or well and satellite will be about 0 or 0.1 to 2 miles. And then from battery or satellite to the gas plant is 1 to 10 miles. It can be satellite. Okay. So you may sell gas at satellite and move all that gas from the satellite to the gas plant directly. And later on, it may need the fuel compressor. Okay. For Anton-Irish, it's about 1 to 5 miles from the battery to the fuel compressor. And from fuel compressor to gas plant, maybe 10-20 miles. We will have many fuel compressors, okay, and we have a lot more tank battery. Good. Okay. Pressure guideline. For the pressure, tank battery, Anton-Irish you may guess or may think that gas enter the battery at about 75 psig. Okay, and from battery, it takes 1 to 5 miles to the fuel compressor. So it leaves the battery at about 45 psig. So it has some pressure drop within the battery. And from the battery, can you give him one more copy? And from the battery, it goes to the pipe. Okay, pipe to the fuel compressor. So it will be about 20% pressure drop. Okay, this is just a guideline. So when it enters 45 psig, it drops to 36 psig, and then it arrives at fuel compressor. And from the fuel compressor, it increases the pressure maybe to 200 or to 400 psig, and gas will travel about 10 to 20 miles more, and then reach the gas plant. When it reaches the gas plant, the pressure may drop about 20%. Okay, and it becomes 160 to 320. That's for Anton-Irish. But this is not like a hard number that has to be like this. No, it's not like that. It's just a guideline. Gas plant may have some other strategy. This is not the only solution, but it's just one of the solution. Yes. Gas plant can take it at low pressure too, like 15 psig. Okay, but in Anton-Irish, okay, everything after the including the orifice meter and everything else, this part owned by gas plant. Okay, before the orifice meter owned by tank battery. Okay, that's why orifice meter and equipment downstream of that are owned by gas plant. Okay, so gas plant has a couple options. Okay, one option may be like in Model 1, Model 2 that put the compressor in the gas plant itself, or may put the fuel compressor. Okay, that's the option. And this is a typical cell diagram. Okay, so for EcoFord, it doesn't have fuel compressor at this moment. It may have later on. Okay, when the pressure is too low. And gas plant has an option to put the fuel compressor out there, or just take at low pressure and put the compressor in the plant. Okay, for the pressure for EcoFord in the battery, okay, or satellite, if you leave the satellite and it can go directly to gas plant, and you expect about 20% pressure drop. Maybe from 250 it dropped to 200, or if you do 500 it dropped to 400. Okay, the guideline is about 20% pressure drop in the pipeline. So when I tell Jason go from what 5 to 100, don't take that, change it. Okay, just 20% pressure drop. Good? Question? No question? Finish the homework and submitting, okay? Multiphase flow. Today we will move on with multiphase flow. Okay, we already talked about liquid hold-up. Okay, we talked about liquid hold-up, flow pattern. Okay, and what else did we talk about? You know the difference between slip and no slip. Do you? Okay, let's test. Senior, what is the difference between slip and no slip? Bubble flow has slip. I put the slip occur in bubble flow. In this bubble flow, there's no slip. What does it mean, Senior? Slip mean what? No slip mean what? Okay, 0. Move on. Trace. 0 2. Gideon. Oh, okay. So if there is a slip, the actual gas velocity in the pipe and actual liquid velocity in the pipe will be different. But if there is no slip, the actual velocity will be the same. Okay? Okay, 1 for you. Good? So can you do the test? Are you ready for it? Okay. So we talk about slip, no slip, and flow pattern for this bubble flow. And we talk about superficial velocity. Mateo, what is the formula for superficial velocity? No clue. How about this? More clue? That one. Could you please read it for me? Okay. You need to know this by yourself. You have to memorize this because it's used for reading the flow pattern map. That is a flow pattern map. And if I want to know what is the flow pattern that I should expect, first I calculate superficial velocity. For this case, it's oil water, so I calculate superficial velocity of oil. I calculate superficial velocity of liquid. Then I look in the map. Okay. So superficial velocity is the apparent velocity if that phase occupies the whole space. So that phase means if you think water occupies the whole pipe, so it will be volumetric flow rate of water divided by the whole pipe area. Good? Mateo, you got this? Yes, it is. It should be very likely to be in the exam. So you should be able to read the flow pattern map. So if I tell you flow rate of water, flow rate of oil, pipe cross-section area, and they give the flow pattern map, you should be able to tell me what is the flow pattern map. So ST is stratified flow, okay? ST and MI stratified with mixing. So if you get DW/O and DO/W, you should be able to tell me the full name. If you say DW/O and DO/W, you get just half point or something. But if you tell me this burst of oil in water and this burst of water in oil, maybe that's full point. Okay? Good? Can you read the flow pattern map? Question? No question? No question. Okay. DO/W. What is DO/W? This burst of oil in water. I need a full name. Okay? To make sure that you know it. Liquid Holdup. Okay. Slip, no slip. Most of the time when there's a slip, V gas is more than V liquid. The only case when liquid velocity is more than gas velocity is for downward flow. When we have downward flow, it is possible that actual liquid velocity to be more than gas velocity. Okay. Another thing that you need to know is how to calculate. No slip liquid Holdup, lambda L. Do you know this? No slip liquid Holdup is the liquid Holdup estimated based on the assumption that there's no slip between two phases. The actual velocity of gas and actual velocity of liquid is the same. So the formula is liquid flow rate divided by total flow rate. And the unit has to be the same. And those flow rate has to be the in situ flow rate. The actual flow rate in the pipe, not the standard cubic foot or anything. It has to be actual flow rate in the pipe. For example, QL, you have cubic foot per second, it has to be actual cubic foot in the pipe per second. And for QG, gas flow rate, it has to be actual cubic foot per second. So Q has to be the actual volumetric flow rate in the pipe. At the standard condition, gas coming out and it's expand, right? So don't use that. Use the one that is actually in the pipe. Or you can do VSL divided by VSL plus VSG. Okay. Same thing goes for superficial velocity. When I calculate superficial velocity, let's say VSG is QG over A pipe. So that QG has to be actual gas flow rate. And A pipe has to be unit consistent. So if this is cubic foot per second, AP has to be square foot. And VSG will be foot per second or something. Good? Next one is about the concept. Okay. Most of the time, V gas is greater than V liquid. Actual velocity of gas is more than liquid in most cases, okay, except double flow. For horizontal, near horizontal upward, vertical flow, we have gas velocity more than actual gas velocity more than actual liquid velocity. So you will expect actual liquid Holdup, HL, greater than no slip liquid Holdup. Memorize that. Okay. Can you? Yes? It is important because we can get the minimum hydrostatic head. Okay. Let's say you have two-phase flow. Go up in the well. Okay. For the flow in the well, the most important pressure drop is about hydrostatic head, right? That is like 85% of the pressure drop. So this means in the well, if you want to guess what is the hydrostatic head, at least it will be equal to what? Then we can use lambda L. Okay. The actual liquid Holdup will be more than lambda L. Okay. So the actual hydrostatic head can be more than the calculated value based on the no slip Holdup. Good? Did you memorize that? HL greater than lambda L for horizontal and upward flow. For most cases where gas travels faster than liquid. Okay? And VSL QL over AP, VSC QG over AP. This is based on the actual volumetric flow rate. Okay. And okay. Slip condition, we talk about V slip is defined as actual velocity minus actual velocity of gas minus actual velocity of liquid. Okay, now VL is the actual velocity of liquid in the pipe, and VSL is the superficial velocity of liquid in the pipe. Chain. Which one is more? VL? Is it more than VSL? Yes or no? True or false? VSL is superficial. VL is actual liquid velocity. Minus 1. This is correct, okay. Plus 1, alright? So actual velocity is more most of the time. Okay? Look at this. Actual velocity is the actual flow rate in the pipe divided by cross-section area occupied by liquid phase. Okay? And cross-section area occupied by liquid phase is less than the pipe area. The formula for VSL is QL over AP. But the formula for actual velocity is QL over AL, area occupied by liquid phase. Area occupied by liquid phase is going to be less than the whole pipe area, right? Whole pipe area is more than area occupied by liquid phase. So denominator is lower, so the total value VL is more than VSL. Got this? The same thing is true for VG. VG is greater than VSG. Who missed the class? That's not done yet. So this means superficial velocity is, for two-phase flow, is the minimum possible actual velocity. The actual velocity won't be any slower than that, regardless of the flow direction, okay? The superficial velocity is lowest possible already. The actual one can be faster, or should be faster, especially when liquid holdup is between 0 and 1. Good? And you may, AL, area occupied by liquid phase, can be expressed as liquid holdup multiplied by pipe area. Question for me? No question. Let's move on. Okay. Oh, okay. This formula is about area occupied by liquid phase is A pipe multiplied by holdup. If you want the gas, it's A pipe multiplied by 1 minus holdup. Okay. Empirical model. We don't cover how to do the calculation of empirical model because it is useful, but it's not that accurate. I'll show you the more accurate one. Okay. The model can be no slip, no flow pattern. We consider this as category A. Okay. No slip, no flow pattern. In this model, everything assumed to be homogeneous mixture. Okay. And the mixture friction factor is used to do the calculation. So homogeneous model or no slip, no flow pattern model, this one works very well for what flow pattern? Okay. Behind Mattel, what's your name? What's your name? Taylor? Okay, Taylor Davis. Right. So no slip, homogeneous mixture work very well for what flow pattern? Bubble flow, slug flow, churn flow, annular flow, disperse bubble flow. 5 choices. Which one? Disperse bubble flow. Correct. Homogeneous model work perfect for dispersed bubble flow. Okay. Homogeneous model. Okay, next, harmony. Homogeneous model work for what flow pattern in horizontal flow? Stratified, elongated bubble flow, slab flow, annular flow, which one? Dispersed bubble flow, yes. So homogeneous model work perfect for that case. Either the mechanistic model or empirical model both do the same thing. If it is dispersed bubble flow, use homogeneous model. Assume that both phases mix together completely, and then the average viscosity and average density is used, and the calculation is like single phase as usual, no problem. Okay. All right. That's a homogeneous model. It doesn't have any flow pattern consideration. This means if I have slab flow, I have this one, slab flow, or if I have annular flow, I can still use homogeneous model, but it's not going to be accurate. Okay? Because my liquid Holdup is lower than usual. Make sense? Homogeneous model use no slip liquid Holdup, use lambda instead of h. So when I use lambda is less than h most of the time, except double flow. So for flow in the well, if I use homogeneous model, my liquid Holdup is lower than usual. So this means hydrostatic head is lower than usual. Okay? And density thing is big deal. So it will give me a wrong answer. Alright. The next empirical model is with slip, but no flow pattern correlation, no flow pattern consideration. It's a little bit better. And the next model in category C is have slip and flow pattern consideration, but it's still not quite good. I present to you mechanistic model, better than A, B, and C. Okay, it is a model based on momentum and force balances equation. Nevertheless, closure relationships are required or developed empirically. Okay. So there's still some empirical data. Okay, we need some correlation in it to do anything. For example, if I want to do pressure drop calculation for annular flow, I use mechanistic model. But inside the model, I still need to have some kind of closure relationship based on experimental data to predict the film thickness, for example. If I use mechanistic model for slug flow, I need to know slug frequency, how many slugs come per minute or per second. I need to know slug length. I need to know liquid Holdup inside the slug body. Those are from closure relationship inside the model. Okay? But it's not pure empiricism. It uses force balance or momentum balance to develop the model. So, okay, next, Emily, right? Between category A model, category B, category C, and mechanistic model, which one gives the most accurate prediction? Oh, okay. Very good, correct. The exam is that easy, okay? You can answer this, it should be fine. Okay, no slip model. From time to time, we use this, and you use it in homework 6 already, okay? No slip model means HL equal to lambda L, okay? So we estimate the liquid Holdup based on QL divided by QL plus QG, and QG is the actual volumetric flow rate, okay? So what you will need to do is, if I give you actual flow rate of liquid, okay, and standard flow rate of gas, you have to be able to convert the standard flow rate of gas to be the actual flow rate of gas. So when it's in the pipe, it's kind of shrink, right, to the pipeline pressure. Can you do this? PV equal to ZNRT. You can do it, right? Can you convert standard volume to be the actual volume? You should, okay? All right. No slip model. If it is for, we can use it for oil, water, and gas liquid. For oil, water, it works perfect for this case and that case. Either this was of water in oil or this was of oil water, it worked just fine. Okay, very good. I mean, accurate, very accurate. Okay, for no slip model, if the actual flow pattern is fully mixed. What do we do for oil water? So step one, we need to know lambda, no slip liquid Holdup. No slip liquid Holdup. In this case, I use HW, Holdup of water. Okay, next, what's your name? Ryan Spot or something? Ryan, how do I get HW for no slip model? That HW. Don't know, skip. So HW is based on flow rate of water divided by flow rate of water plus flow rate of oil. Good? Okay, now you can do it. So the density, mixture density is a weighted average of oil density and water density based on the Holdup. Holdup is a value between 0 to 1. It's equivalent to volume fraction. Okay, Ryan? You can do this? Yes, okay. So density, we can do weighted average. But viscosity, most of the time, it will be more accurate if we use this formula to do the calculation. If we do weighted average based on the Holdup, this means water viscosity is 1. Okay, 1. This is water. Okay, H2O. So pure water viscosity is 1. Oil, I have viscosity maybe 10 centibar. The viscosity of mixture between oil and water is not in between, it's not like linear interpolation. That is wrong. Okay? When we add a little bit of water in oil, the viscosity go up, it doesn't go down. Okay? Most of the time. So we use Brinkman correlation. Brinkman calculation is viscosity of mixture equal to viscosity of the continuous phase multiplied by 1 minus Holdup of the dispersed phase. Okay, if I have water in oil, a little bit of water in oil, so mu C will be what? What's your name? Alina or what? Alina, what is mu C for water in oil? Oil viscosity. What about HD? What will be HD for water in oil? Holdup of water. Volume fraction of water, very good. Okay. And then we can calculate mixture viscosity. And the rest is the same as single phase flow. Okay? So next, is it Alina too? Oh no. What's your name? Mackenzie. How do we do the single phase pressure drop calculation? What's the formula for frictional pressure loss? With fanning friction factor. Minus dPdL equal to what? Next, what's your name? Mackenzie. Frictional pressure loss in terms of, what do you want? Fanning friction factor or you want Moody? Any of them. Fanning friction factor is minus dPdL equal to, you don't remember? Next, what's your name? Brandon, do you remember? Next, what's your name? Jeremy. No, not Jeremy. Who remember this? Who memorized it? Okay, F, everyone. You take F. Who memorized it? No one? What? It has to be F. How about this? For finding friction factor, 2F rho V square over D. That is for finding friction factor. Do you want to repeat after me? 2. Come on. 2F rho V square over D equal to minus dP/dz. Okay, you got it, right? This is just frictional pressure loss. And you may have to do this several more times until the test day or something. Alright, so we know how to get the fluid property for the case of two-phase flow. What about gas oil? For gas oil, it's easy. Everything is just based on the weighted average. It's a weighted average based on the Holdup. Okay, everything is a weighted average based on the Holdup. Okay. Density, viscosity, and sigma. What is sigma? Okay, next to Jeremy, what's his name? Eric, what is sigma? That's sigma. The unit is Newton per meter. What has the unit of Newton per meter for fluid property? Or millinewton per meter? Can it be something has to do with surface? Surface tension. Surface tension, okay. Sigma G. Okay. So you do kind of weight. Actually, you don't do weighted average. If you have three-phase flow, then we do this. For two-phase flow, just use surface tension of oil and water, oil and air. Okay, that's the surface tension. It's just one value. This is maybe. Let's delete this for now. For surface tension, we don't do a weighted average like that. Okay. Method of calculation: total frictional pressure loss has to consider frictional pressure loss, gravitational pressure loss, and accelerational pressure loss. Most of the time, we don't do every term. We may neglect some term, and our answer may still be acceptable or may still be accurate enough. But we need to know when to neglect it. Acceleration term is negligible except at low pressure, less than 100 psi. Or if you have choke, expansion, or third, then we don't want to neglect accelerational term. Okay. In well, elevation term dominate. About 85 to 100% is the elevation frictional pressure loss. dP/dz sub G, that's elevation term. Okay. Or gravitational term. In pipeline, elevation term is about 0 to 30%. Friction term dominate, okay, 70 to 100%. So if we get friction term right, the answer probably is almost correct. Okay. Martina, who get the exam homework for her? Afshin? Okay. Who else missing? Matthew D. Sander. Who get homework for him? Or no one? Who's his friend? Who have it? Do you have extra? I don't have any extra. Who have several copies? You take it?
Yeah.
Oh my god, you take everything actually. Okay. Who else? Okay, how many did you write at 10, 11, 10? I think it is. We'll talk more after class, okay? Okay, that's it. The equation that you should memorize is 2 of them. 2F rho V square over D. That's frictional pressure loss based on fanning friction factor. Accelerational pressure loss is rho G sine theta. And in this class, theta defined not like in drilling. Okay. In this class, theta is the deviation from horizontal direction. When theta equals to 0, this means horizontal flow. Okay, sine 0 is 0, right? So gravitational term is 0. When upward flow, sine pi over 2 is 1. Downward flow, sine pi over 2 is minus 1. So when we do downward flow, we have gravitational pressure loss to be negative. Okay. Behind Eric, what's your name?
Graham.
Graham. What does it mean for negative gravitational pressure loss? Did I just do wrong or what?
Sorry?
Negative
Yeah.
gravitational pressure loss. What does it mean?
Means it's helping you.
What?
Means it's helping you.
Yes, I gain pressure. I didn't lose pressure. Okay. So this is the equation. Just like single phase flow, you may use Highland equation. In the exam, of course, there will be somewhere that you have to do that iteration thing. Be ready for it. Okay. And if I give you the equation like this, you have to automatically know if it is fanning or moody. And you have to know if it is for laminar or turbulent. F equal to 16 over Reynolds number is for what, Graham? Laminar or turbulent?
Laminar.
Very good, correct. I checked Highland equation versus Colebrook. It's just the same. Okay. Empirical correlation category B. Category B has slip but no flow pattern. Okay. We don't use this at all, but one thing to mention is Hagedorn-Brown, because if Hagedorn and Brown get a lot of data, okay, based on data obtained from 1,500 feet deep vertical well, okay, and it's a real data, 360 data point. So Hagedorn and Brown get a lot of data. No liquid measurement, something, but it's important data to talk about. So in this model, we have slip consideration, and the pressure gradient is have three terms add together, or this category C, okay. That's Hagedorn and Brown has a lot of data, and it is in category B. That's it. No calculation or anything short. But if you have your calculation from Hagedorn and Brown, and you have your calculation from your mechanistic model, and it's far away from each other, probably mechanistic model is wrong, or you input something wrong. Okay. So mechanistic model, even though it's more accurate, but it's more difficult to put the number in correctly. Okay. So empirical model, even though it's not that accurate, but it can give you a quick check. All right. Buy the book for more information, and we don't cover it in class. So category C, with slip with flow pattern, there's equation E sub k value that is to account for any acceleration. You see, F rho v squared over 2d, that is frictional pressure loss, rho g sine theta, frictional pressure loss, and the denominator 1 minus E sub k, that is to account for any acceleration or pressure loss. Okay, that is Beck and Brill. Okay, comparison between unified model, Xiao et al., 1990, and there are several statistic parameters, epsilon something, 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 something. Let's take a look at epsilon 2. Epsilon 2 is prediction minus measurement over measurement, okay, multiplied by 100. So it's a percentage, average percentage error, or we call average absolute percent error, okay. So by looking at epsilon 2, just epsilon 2, okay, the model that have lowest average absolute error is this model. This model means Xiao et al., 1990. Okay, Beck and Brill. So this is for certified flow prediction. Okay, just certified flow prediction. Beck and Brill has somewhat more error. McCritchy Brill, more error. Douglas Eden, more error. So mechanistic model give very good. Take a look at the number. When I said very good, it's still 34% error. And 34% error. when I say, hey, mechanistic model give a good prediction, it's not like plus minus 0.01 relative error. No, 34, very high. So if you design a pipe, or you design some pressure drop calculation, you need to make sure that, hey, what if the simulator give you 34% error? Can you handle it, or the pipe just break? Okay. If the pipe just break, it's not good, right? So anticipate that the prediction can have 34 or maybe more error. Okay, 34% error or 35% error is on average. Okay, on average. So this means sometimes maybe 20, 25, sometimes maybe 40, 45 or something. It can be more. Okay. The rest is error with the unit. Okay. Minus 3.2 times 10 to the power 4 Pascal or something. Okay. This is a comparison for intermittent flow. So next to Graham, what's your name?
Ryan.
Ryan? And Ryan too, right? Okay. Okay, Ryan, what's your last name?
Baxter.
Ryan Baxter. What is intermittent flow? So intermittent flow for horizontal flow can be in the form of slab flow and what else? Slab flow and E something, E what? Elongated bubble, okay. Can be slab flow and elongated bubble flow. So for vertical flow, it can be churn flow and slab flow. So when I say intermittent flow, it already includes churn flow and slab flow for vertical flow. Or horizontal flow can be elongated bubble flow and slab flow. Okay. So for intermittent flow, unified model do good, right? 22% average absolute error. Okay. Annular flow, not quite good, but still better than other model. Okay. That's annular flow. And overall performance is better. Okay. Well-ball model. Look at this picture carefully in the well-ball model, and you will see that in the well, even though we have just one well, it can be several flow patterns inside. Okay, several flow patterns can coexist, but at the different location. It happens like this because gas expands. So in well-ball model, there has to be some iterative approach. Okay, like what you did in homework 6 or something. Remember that you have to iterate. Okay, and you go right and up and up and right, 2 different cases, and then you divide it and iterate. They do that in computer program. Okay, so we compare title or comprehensive model, use a combination of several mechanistic model all together. Okay, mechanistic model put together become comprehensive mechanistic model. And the researcher who do that is Ansari and co-worker. So when we compare with other flow model, let's see the result, comparison result. We have Alves, 1991, Wallis, and several other model. So this is column 1. So this is relative performance of Ansari model. Okay, lower number is better performance. So low is better. Mechanistic model, the number is 0.7. Hybrid and bow is even lower. So hybrid and bow is better. When we compare all the data bank, okay, but it's not quite a fair comparison because hybrid and bow has like many data points. Okay. So there's a column, vertical, no hybrid and bow, column 4. So in column 4 is a comparison without hybrid and bow. Look at hybrid and bow. Hybrid and bow, it works good for itself, but it's not as good as mechanistic model when we try to do some prediction other than hybrid and bow data. So in conclusion, mechanistic model is the best. Okay, even for vertical flow. Let's talk more about How do we do the calculation conceptually when the well look like this? You see this one? Different location has different flow pattern. Different location has different fluid property, different pressure, different temperature. So what we have to do is iterative method. Number one, they have to specify the fluid property at the inlet or at the bottom of the well. Okay? Calculate the pressure drop. Once I calculate the pressure drop, then I get the fluid property at the next location based on the pressure and temperature that I calculate. Then I calculate the average property and then I iterate and go to the next section, next section, next section. This kind of thing is similar to what you did in the homework. Is too much for the exam. Okay, so I don't put it there. But just to show you, there are many equations. Okay, the change of temperature with length, the change of pressure with length, the change of mass flow rate with length, the change of mass flow rate of liquid with length. Okay, the change in the phase composition with length. Composition of liquid phase also change with length. That's the change of composition of gas. For example, you may have 5% C2, but when we move up a little bit, we may have less C2. Instead of 5%, maybe 4% or something. So the composition of gas itself also change with the location, right?